another of your favorite episodes in AP Statistics. This is something you've all been waiting for, normal distributions. All jokes aside, this particular chapter is going to be super important. This is going to set everything up for what's to come. If you're going to put some effort into one chapter this semester, this probably needs to be it, right? Don't get me wrong, there's harder stuff that we're going to do, but this one's going to set the tone, and it's going to continue to show up as we come back to these just distributions as we kind of start working with them. What you see here is what we have is a normal curve, right? Normal distributions are something called where we have single peaked bell-shaped curves, right? It's what we think of as a bell curve, right? Normally distributed distributions. Now, these things are, when we say the word normal, that is such an overloaded word. There is so many things that go along with that. Number one, it does talk about the shape, right? It is a bell-shaped type of curve, but it's also talking about lots of other things. For example, when we say normally distributed, we're not just implying it has this particular shape, but it also has a particular set of distributions. It's spread out in a very, very specific way, and it is the way you see on the screen right now, right? This is something you probably have already seen before. This is your normal distribution. This is what we call the empirical rule, or the 68, 99, 95, 99.7 rule. The things that you're probably familiar with are the numbers inside here. Now, these are things that you definitely need to memorize. You should use it enough that it's probably just going to automatically get memorized, but just in case, make sure you memorize it. This is not on any of our formula sheets, by the way, which you will be getting this chapter. What I want to call your attention to is up here on the top. 68% are within one standard deviation. It means that when I look at my distribution, when I look at all my percentages, all the stuff that I collected, all the data, I know that 68% of the results that I got fell in between one standard deviation above and one standard deviation below, right? If we took the mean, we added the standard deviation and subtracted it to get these two values at the bottom, if it's normally distributed, we know 68% of the data falls in there. And if I go all the way out to two standard deviations on both sides, that's 95% of all my data. If I go all the way out to three standard deviations on both sides, that's a really far distance in terms of away from the mean something is, right? This is in outlier territory, right? And technically, for normally distributed things, we use two standard deviations away. If it falls outside of two, we say it's unusual. If it's outside of three standard deviations, we say it's an extreme value, kind of like how we had defined it earlier with outliers and extreme values. If I have 99.7, that means there's only 0.3, not 3, but 0.3% that fall outside that three standard deviations away from the mean. These curves are called density curves, meaning because the area under the curve is exactly 1 or 100%, however you want to think about that. Normal curves are defined, they're created by a mean and a standard deviation. You give me a mean and a standard deviation, I don't care what they are, I can create a normal model to describe that. Now that doesn't mean that model is always normal, right? The distribution, the way things are falling away from that mean have to fall away in a specific way. But there exists a normal distribution for every single mean and standard deviation you could come up with. Let's define a few things, all right? We've been talking about standard deviation as a measure of spread, and it definitely still is, right? We are now talking about the quintessential normally distributed bell-shaped symmetric unimodal curve that we can. It's called the standard normal distribution, or the standard normal curve. Well, the unit of measurement, like when we put 1, 2, 3 on the bottom, right, we mean one standard deviation, two standard deviations. And for curves, standard deviations can mean 10, could be 5, could be 0.2, right? The distance away from the mean is very relative to whatever your values are. Let's talk about the properties of standard deviation. These are probably some that you already know. Obviously, the larger my standard deviation gets, the wider my spread gets. That doesn't change the fact that it's normally distributed. It can still be normally distributed and very wide. It's about that percentages and how it falls apart in there. My standard deviation, we already said this, if it's 0, it means every single observation is the same value. It doesn't have a distribution. In fact, it's not distributed at all. It's the same thing. It would not be considered a normal model. They have no variation. Number 3, S, standard deviation, is influenced by outliers. It is non-resistant, just like the mean is. But we are talking about a normal distribution now, so we're not really worried about skewedness at this point, but you can definitely have a little bit of outliers. And we are okay with some skewedness, right? But not major skewedness. We're not okay with major outliers. And we'll kind of talk about the different varying levels of that. Obviously, we just saw the curve. If the data is normal, we can divide it up into those specific percentages, and those are called the empirical rule or the 68, 95, 99.7 rule. That's just a lot. That's a mouthful. 68, 95, 99.7. If you like that, you can always say that, but I tend to say empirical rule. It's just easier to say. So make sure you kind of lock those two things in your brain together at this point, so you know what I'm talking about when I say it. Let's do some examples and kind of illustrate what we mean in terms of how does the standard normal model work, what is it useful for. Before we get into the percentages, because I think that part of it's actually really easy, let's talk about Z-scores. A standardized value, also known as a Z-score, tells me the number of standard deviations away from the mean we are. So here we have an example where we have a track and field event consisting of 7 different events, right? You have runs, you have hurdles, you have shot puts, javelins, all the above, right? Long jumps. The question is, if you have all of these different events and they have different ways of being measured and different ways of winning, sometimes it's a low number is a better one, sometimes a high number is a better one, how do I score them? How do I determine which score is better than another score? So in terms of when I put it all together, how do I score it in a way that is consistent, right? Because we have different units, it makes it really awkward, right? And so we're going to use what we call a standardized score. So the units don't matter. And so we do that by creating a standardization, basing everything on a mean and standard deviation, because what we have here is a way to strip the units away and just look at how far away from the mean something is. The farther away from the mean you are in the right direction signifies a much more significant score. So here we have the 800-meter run was 8 seconds faster than the mean for that particular year. The winning long jump was 60 centimeters longer than the mean. So we're kind of stuck. We have different units. One of them is a measure of time, one of them is a measure of distance. I don't know how to give one thing a score or a better score than another. So we're going to use a Z-score method to figure out which one deserves more points. The way we do this is we need to standardize it. And we're going to do that is we're going to say that we know that these things follow normal distributions. And so we say that farther up the line, the farther away from the mean you are, the better it is. And we're going to use the standard deviation as that unit, that measurement. So if you're 1 above, you're 1 standard deviation above. Let's find the Z-score for this one. We have a mean of 137 seconds. We have a actual time of 129, and then our standard deviation is 5. If we want to know the Z-score, this is it, right? So you're looking at this is in words, not in symbols. If you look in your book, they'll have, I think, Y hat and Y bar or something like that. I typically say X for this one. This is your mu, your mean, and then the standard deviation, which is S or sigma on the bottom there. You look that up in your chapter. You'll see a lot of different versions of that. They're all the same thing. We know that we subtract the value minus the mean divided by its standard deviation. It's going to tell us the number of standard deviations above or below the mean. In this example, we have our value of our winning value minus the average divided by the standard deviation. That gives us negative 1.6. Yes, Z-scores can be negative. What that means is that the number you are working with, in this example it's 129, is 1.6 standard deviations below the mean. That's what the negative signifies. Right? It can be positive, being above the mean. In this example, or in Z-scores in general, negative or positive isn't a good or bad thing. It simply means that that's how many standard deviations, and the direction is contained in the sign. Positive is above, negative is below. So if we look at the other score, right, the long jump data, it was 60 centimeters longer than the mean, and the standard deviation is 30 centimeters, right? So we bring this up. The actual score for this, let's look at our other one. We have the original, which is negative 1.6, and we brought in 660 was the actual winning long jump, and the average was 600. Divide that by the standard deviation. It turns out it's 2, but this is negative 1. Wait a minute. Positive, negative. How do we know which one's better? Right, which one gets more points? Isn't positive or negative a good or a bad thing? Keep context in consideration. We know that these are both scores in the better direction. We know that scores for time running, we want lower scores. So this is actually in a good direction, right? So the fact that it's negative isn't really important. This is, the longer the jump is, the better it is. So I'm going to look at just the absolute value of this. Now, sometimes being negative is a bad thing, right? If I was looking at the high jump as a negative score, it means I'm looking at a number that was below the mean. So then, in other words, it wasn't even an average jump, right? It was less than the average, because negative in this example would be a bad scenario. But either way, 2 standard deviations is farther away from the mean than 1.6. So the high jump gets the better score because it's farther away from its mean than the one for the 800 meter. Another way of looking at z-scores is to compare things that don't have common units, like the SAT and the SAT. Right? ACT is out of 36. The SAT in this example was out of 2,400. And so if somebody said they had a 2,000 in the SAT and somebody else says I've got a score, a 34 on the ACT, which one's a better score? Well, that's actually dependent on what the averages and the means were for that particular year. We're going to pull these things up. These are actual values, and we're going to see what happened, right? Who's got bragging rights? Now, I kind of think the 34 does to start off because it's a lot closer to the max than the 2000 is, but I'm not sure if 400 points on the SAT is equal to 2 points on the SAT. Let's find out. If we work out the z-scores, now remember, higher score is better in both examples. And it turns out this is almost 2 standard deviations above the mean. A good score, but 2.5 standard deviations is an even better score. So the ACT person in general did better for his test or her test than the person that took the SAT. So keep that in mind. This example, we're looking at going in the same direction because we're looking at higher is better. The SAT is not as good as the ACT. So here, the ACT has the bragging rights, right? And we did this by just finding the standardized value, or what we call the z-score. Percentiles, last thing. There's a couple of things you want to make sure to look up in your book. Number one, the calculator functions that are going to happen here, and this is important. This chapter is a big deal. Okay, it's going to set the tone, and the things that we're going to be using a lot. It won't be so much every chapter, but eventually you're going to see this thing start to show back up. So make a good effort to learn this stuff now. We're going to look at normal CDF, inverse norm, and something called a normal probability plot. Those are your 3 new things in your calculator. In your book, it talks about TI tips. There's a section called TI tips in your text. Definitely check that out. We will definitely be going through this several times in class, but having an idea of what's going on is going to make it a lot easier for you to follow. So let's go back. If I said I scored in the 97th percentile on the math portion of the SAT, that means that I scored better than 97% of the people that took it at the same time that I did. All right? You scored better than 97% of all the people that took it at the same time you did. Equal to or less than, right? So if you were looking at your curve, it's 97% of the area under the curve or less, right? So all the area to the left is what we call a percentile. If I said you scored in the top 10%, that would mean there's 90% of the area to the left of your curve. That means you scored in the 90th percentile, right? Percentiles, quartiles, like we talked about Q1 and Q3, those are all different kinds of percentiles. When we're working with normal CDF and inverse norm, percentiles are going to be a thing that we're going to find out, the probability of something occurring given a certain scenario. Those are all things we're going to be looking at. You can find this in Canvas as well. The homework is on out of your book. These are the textbook problems. We're going to be looking at those kinds of things over the next couple of days. So definitely take a chance to look at those. Definitely check out the calculator part of this, and hopefully this is starting to make a little bit more sense if you were starting to read the book. Definitely highly recommended to read this chapter. I will see you guys next time. If you have questions, bring them to class or send me a message.